If you're online now, we'll just give it a short time more for more people to attend and settle in, and then we'll get our webinar underway. Okay, well, welcome to the NHP webinar program. Today we'll be examining the emergence of high-efficiency IE3 motors in our industry and looking at the effects they may have on protection and control switchgear. If you have a question during the webinar, feel free to use the Teams chat function. We have some industry experts mediating and standing by. I'll be on live for a short time following the presentation, should you wish to have a couple of questions answered live online. My name's Steve Young. I'm a technical training leader at NHP. Been with the company for 35 years, so I hope we find out some informative things about switchgear and the way that it reacts with our selection of motors. So some of the subjects covered will be of the history and the introduction of the IE3 and IE4 motors for industrial use. The MEPS program, or Minimum Efficiency Performance Standards, in Australia and New Zealand, covers this range of motors. We'll look at some of the more important motor characteristics and examine the operation of circuit breakers and contactors. And we'll look at their expected behaviours and duties when used in direct online applications in conjunction with the IE3 and IE4 squirrel cage motors. Well, the introduction of the IE range of high-efficiency motors worldwide has been an active program since around 1998 in the European community. Regulations for Australia came into force around October 2001 for the introduction of MEPS series and the MEPS 1 motors as standard efficiency motors. The introduction of MEPS 2 started around December 2003, and regulations to AS/NZS 1359.5 2004 actually came into force around 2006. The IE2 motors were roughly designated high efficiency motors as a generic term, and the IE3 series of motors began their introduction into Europe around late 2009 from all of the data which can be reliably sourced. Introduction to Australia has been roughly estimated at early to mid 2010. Each motor design was based upon BAT, or best available technologies. Now, the designs for each subsequent range of these motors is still based on the best available technologies for manufacture of the components and designed to increase the operational efficiency characteristics. The full evolution of the program in Europe is ahead of the uptake of the program in Australia and New Zealand. However, this is a rough timeline with some numbers attached to consider. We have the generic terminologies of high efficiency as IE2, premium efficiency as IE3, and super premium efficiency as IE4. The IE5 and ultra premium and reluctance motors are not considered in our subject matter today. These classes will always be operated with VSDs. Since 1990, where common efficiency was around 90%, we've progressed to IE4 motors with efficiencies of 95.8%. The largest jump in efficiency was around 3.7% between the IE1 and IE2 motors. IE2 to IE3 brought us 1.2% increase, and the IE3 to IE4 has brought us just under a 1% increase in efficiency at rated speeds. The increase in the efficiency was gained by cutting motor losses in the design and construction. Now, this included technologies to reduce the thickness of core laminations, to reduce eddy currents, and to reduce iron losses. The motor also has more copper in the stator and an altered winding geometry, and this reduces impedance losses as well as increases the size of the rotor copper current for the same reason. Other improvements are mostly mechanical, such as low friction bearing design, fan design and airflow cooling efficiencies. All of these improvements are a winner when it comes to theoretical efficiencies to hit a brief. However, they come at a financial cost as well as some performance costs. So what happened as a result of the new design of these motors? Well, starting currents to nominal full load current ratio increased. Peak torques compared to nominal torques increased. Slip at rated power decreased, making the rated power delivery closer to synchronous speed. Power factor at the rated power decreased. Thermal utilisation decreased. That's a plus. Rotor inertia increased. The entire motor weight increased, and of course, the price increased. However, along with all of these factors, a number of key characteristics changed. As with earlier design motors, there are different speed torque characteristics for each particular style of motor. Now, one of the most common issues with high efficiency motors is their lack of torque between 10 and 60% of the speed. You can see on this graph here the difference in the speed torque characteristic. We've got the operational speed, there's the vertical blue line at the end there. You've got the current speed curve, is the current line with the green, and the torque speed curve in relation is the red line. The characteristic of high efficiency motor may cause it to stall during run-up depending upon the load acceleration torque requirement at certain speed, and it's all dependent upon what type of load these motors are pushing. Fans are of particular concern in this area, as are loads that may be called to stop under emergency conditions and asked to start fully loaded. These applications, fairly common, include conveyors, crushers, mixers, and other process machinery. In these applications, excessive oversizing may be necessary to produce enough torque to get the load away. And as far as efficiency at operating speeds go, this defeats the purpose of the high efficiency motor being used in the first place. In these instances, variable frequency drives may need to be installed in order to allow the motor to develop low speed torque during a run-up phase. Pre-MEPS motors had general performance parameters that had remained constant for many years. The IE1 or normal efficiency motors were designated for pre-MEPS motors. The IE2 motors were introduced into Australia in 1990s. These displayed some different characteristics to the IE1 style. Standard squirrel cage type motors displayed locked rotor currents between 4 and 8 times their full load current. All devices that are rated to start and operate these motors to IEC and Australian standards are based upon these types of full load currents and locked rotor currents. They had an AP or a peak inrush current of between 9 and 14 times full load current. Now, I've got to state here right now that peak inrush current has always existed. It's just existed at a different level depending upon the characteristic of the stator and rotor. So with the introduction of high efficiency IE3 type motors, locked rotor currents went to between 7 and 9 times full load current. For the peak inrush went to between 15 and 24 times full load current. Now, one specific example taken from a manufacturer's literature was a 37 kilowatt 4-pole motor drawing 63.9 amps full load current. The locked rotor is quoted at 498.42 amps or 7.8 times full load current. The AP or peak inrush is quoted at 1331 amps or 20.83 times full load current. Now, motor manufacturers are not compelled to publish the peak figures with their other data, and sometimes it's very, very difficult to obtain the official figures. Let's have a closer look at the figures between IE3 and IE4 motors as a general comparison between the two models. And there's not a great deal of difference between the two, as I stated before, about just under a 1% efficiency saving. We did a quick comparison of the frame sizes between IE3 and IE4 motors from WEG Motors. They were kind enough to give us some up-to-date data. And out of that data, I used only 2-pole as a worst case scenario. As we can see here, most of the numbers between IE3 and IE4 indicate that the IE4 model is actually lower in current draw in most of those cases. And all the way up to a 110 kilowatt motor, there's a major difference, albeit a small one. The MEPS requirement for any energy efficiency tops out at a 185 kilowatt motor size. However, technologies have, of course, allowed all motor sizes to be developed in a similar way. The AP figure is the theoretical peak current figure, calculated as locked rotor current times 2 times root 2, or 1.414. This gives a theoretical maximum inrush peak of 22 times full load current. The figures in the bottom row show the multiples of full load current on these peak figures. The multiple of full load current to locked rotor will have a bearing on what the resultant peak number will be up to the theoretical maximum peak. Here's some results of actual site testing from a mine site in Western Australia. This is a conveyor motor. It's a 110 kilowatt, 185 amp full load current and a locked rotor of 1406 amps. The highest recorded phase was 3,750 amps, and this is a multiple of 20.27 times the full load current of the motor. Now, this event can and did have serious effects on the connected switchgear. Might also add that these figures can change depending upon the moment in the cycle that the motor is energized, as well as with the starting position of the rotor in relation to the stator. So every start is going to give us a slightly different answer, or a slightly different set of numbers. So motors must be controlled by switchgear of some type, both for circuit conductor protection, for motor control, and for starting, as well as motor protection. So firstly, let's look at circuit breakers. Now, modern day circuit breakers are what we call fault current limiting types. They react quickly to short circuit currents and rapidly extinguish high currents and limit energy levels flowing into the system that may be damaging to both property and persons. They feature magnetic repulsion contacts to limit high fault currents. They also incorporate bimetal overload detection, bimetal strips. They also have magnetic short circuit coils to trip the breaker contacts. So let's look now at how the breaker actually operates under short circuit conditions. Well, thermal magnetic fault current limiting breakers trip on fault primarily by unlatching the trip lever with the shot pin being forced out of the short circuit coil by a rapid rising current. You can see here the left-hand figure has not got the shot pin extended. The right-hand figure has an extended shot pin. The magnetic forces fire the pin hard enough against a spring resistance to travel the distance to hammer the unlatching mechanism. This process normally begins at between 8 and 15 times the device's nominal current rating, depending upon the characteristics of the breaker's instantaneous trip level. Some breakers have adjustable trip levels, some breakers have fixed instantaneous trip levels. Now, until this event takes place, and that pin hammers the unlatching contact, the breaker contacts will remain in their closed position as far as the preferred position. After this event, the shot pin resumes its latent position back inside that short circuit coil. The fault current limiting action is also caused by magnetic repulsion under short circuit current flow. The two current paths in close proximity to each other causes opposing magnetic forces, and this tries to force the contacts apart. This is in line with Fleming's right-hand grip rule. Depending on the moment of initiation of a high fault level, the extreme current inrush will cause a corresponding spike in magnetic flux between the parallel circuit paths. This will exert pressure on the breaker contacts, and if a high enough current flow is evident, the contacts will be forced apart. Now, the contacts will be forced apart, that will draw an arc between the two contacts. If the duration of the short circuit is long enough, the contacts may trip after the short circuit coil fires the shot pin to release the contact latch. If there's not sufficient energy flowing in the circuit over a long enough period of time, the shot pin may not unlatch the contacts. In this event, the contacts will close again without fully interrupting the circuit. So in the event of a low impedance, high energy short circuit, this is a very rare occurrence, as it would mean that the cause of the fault itself would need to totally clear very quickly to avoid a trip. So there are instances in our industry and in the field where a short circuit occurs, the site of the short circuit blows up, if you like, or blows out before the circuit breaker can actually unlatch, can actually trip the contacts. Everything starts working, the magnetics work inside the contacts, but the actual circuit breaker sometimes does not trip because of the timing of the short circuit. Now that's for thermal magnetic fault current limiting breakers. Let's have a look at electronic breakers. So electronic breakers essentially have the same contact mechanism as the thermal magnetic types. Now, because of this, their contacts behave in the same way when under high fault situations. So the contact separation limits are let through and peak currents. Electronic breakers have an electronic overcurrent relay, and this is fed by tiny current transformers to measure the current in small time periods, and this is measured in milliseconds. This calculates energy. As we know, energy is expressed as current squared multiplied by time. So this detects exceedances of the set parameters in all of the time and current areas. Now, when an overcurrent relay detects an overcurrent, it fires a minute electrical signal to a magnetic hold trigger that allows the contacts to unlatch and move to a trip position. Until this event, the contacts will remain latched closed, and this is very important to understand. The OCR measures according to its clock speed or its scan rate. Now, the Terasaki range of MCCBs and ACBs have a scan speed of between 2 kHz and 4 kHz for the later models. Now, this means that the OCR scans between 40 and 80 times per electrical cycle, per 50 Hz power cycle. It samples and integrates each measurement until a number is reached in each running sequential time period according to the settings. So a sequential time period is a small gap in time which continually moves. So that the amount of energy that's scanned within that small, very, very tiny millisecond time envelope is calculated by the OCR, and it makes a decision. If it exceeds its settings, it will fire off its magnetic hold trigger to release the contacts. If it doesn't exceed it in that running time period, then the contacts will remain closed. So this is the characteristic of the type B MCCB. A small, very small time delay is in milliseconds is incorporated into the trip signal initiation. So the type B are designed to allow for selectivity between at a high level against type A or thermal magnetic breakers. So in other words, the thermal magnetic breaker inherently has a quicker trip function under short circuit than the electronic breaker. Now, a true short circuit event will generally last many cycles, or as long as it takes for the protection device to operate and fully clear the fault. So in the event of a DOL start with IE3, IE4 motors, this high inrush current may manifest itself as a short circuit because of the low impedance circuit will disappear as soon as the motor stator has established a magnetic field and the current starts to flow in the rotor. After this point, the rotor will develop torque and begin to rotate following the rotating phases and polar orientation of the energized stator windings. This is how induction squirrel cage motors operate. This time current graph illustrates the difference in starting current draw between IE2 and IE3 motors. The IE3 motor graph is in yellow. The red time current graph is a typical thermal magnetic breaker rated to start up a 110 kilowatt, 185 amp 2-pole IE2 motor. The same rating IE3 motor, when connected, causes the breaker to trip in more than 75% of the start attempts. And this is before the rotor has moved. Before the motor is actually taken off, the circuit breaker will trip. This is prior to the moment of inertia being reached. Now, the moment of inertia is the quantity of energy required to move a mass from a standstill to a point where it develops torque against its own mass to allow angular or rotational acceleration. That's the definition. And you can see here the inrush of the IE2 motor, 2,590 amps on a 185 amp motor. The IE3 motor, 3,750 amps. And it clearly goes over that vertical section of the red time current graph, and that is the instantaneous trip point of that 250 amp circuit breaker. So prior to this point in time, the supply is trying to produce current in line with Ohm's law. The current flow is dependent on the latent line impedance. The lower the impedance level, the higher the current flow in relation to the voltage. So this condition remains until a magnetic flux is established and stabilizes the current inrush to the stator. We can see here an actual electronic breaker in a motor control center application. And you can see the carbon deposits as a stain on the motor control center enclosure. This is a result of the exhaust from the first attempt of a DOL start on an IE3 motor. The contacts inside physically parted, and we had a large arc drawn within the arc chamber and exhausted into the motor control center. So let's look at the behavior of motor contactor in this application, because we've got a circuit protector being the main circuit breaker, and we'll have a contactor which starts and stops this operation. So contactors are sized and rated for duty according to AS/NZS 60947 Part 4. The utilisation category AC3 is based upon a locked rotor current of 8 times full load current of the connected motor. Now the contactor is fully rated for on-load operations at this level as one of its performance tests. Another test is carried out for its withstand to short circuits. We can see the contacts of the contactor as it operates. As we see the contacts set up of the AC contactor, its orientation, they're effectively butt contacts. These are designed to give limited magnetic repulsion lift during motor starting. Now, should there need to be an interruption during a locked rotor event, there are arcing horns and arc runners provided to direct arcs into the splitter plates in the contact arc chamber. The issue we need to fully understand here is that motor contactors have not been tested against the applied characteristics of multiple DOL starts from IE3 and IE4 motor loads of any size, not just the larger styles. So effectively the contactor will be subjected to a higher than designed locked rotor current and a low level short circuit every time its DOL starts a motor. Because of this, the contactor is way beyond its AC3 duty compliance level. Now, during a motor start, here's another issue. During the motor start, an extremely high transient current spike can cause the voltage in a weak or marginal supply system to drop away to potentially very low levels. Now, in certain ranges of contactors, the voltage drop may cause a coil fluctuation, and this can cause the contactor coil to reduce the closing force on the contacts. So we see here a motor start current and spike in the current. If we have a weak supply, this affects the applied voltage in the system, the standing voltage in the system. In a weak system, that voltage will drop away. If the voltage drops away, the coil has a tendency to de-energize or to try to de-energize with less magnetic force, and of course that's going to lessen the contact force. Now, the voltage drop may cause that coil voltage to fluctuate, and this can either reduce it or cause the coils to actually start to drop out and the contacts to fluctuate. So the contacts will slightly open and cause impulse cycling of the coil's magnet system. This in turn can cause contact bounce in the contact set. This event alone may drastically shorten the life of the contactor. Now, understanding a little about the expected operational behaviours of the connected equipment, what behaviours can we expect when connected to these IE3, IE4 motors, especially in a DOL start application? Our field experience, especially in the mining industry, had taught us many things to help overcome certain issues caused by the extremely high peak current inrush. Firstly, this part of the motor start characteristic has no impact on thermal current settings of the circuit breaker or the motor overload. Secondly, it only has a small impact on the magnetic settings or the characteristics of the thermal magnetic circuit breakers. It has no effect on the settings of electronic overcurrent relay breakers, MCCBs. The major effects are on the contact sets of circuit breakers of all types, and of course of motor start contactors. So let's look at a couple of the findings that we have from the mining industry in Western Australia. I was fortunate enough to spend 7 or 8 years in WA, and we had a lot of experience on this end with our mining customers. The major heartache in the area was caused by certain motor sizes when used on a DOL start. 45, 55 kilowatt, 90 to 110 kilowatt, 200 to 210 kilowatt, and of course larger than that. Although the numbers of these operations at 280 to 300 kilowatt were fairly rare. Now, the reasons for this we discovered were due to the physical frame size of the circuit breaker being affected by the magnetic effects of the peak inrush of the motor. Increasing any of the settings did nothing to stop the breaker from tripping. For these marginal sizes of motor kilowatt ratings, the only way to prevent a trip was to increase the frame size of the breaker. This had the effect of increasing the total mass of the breaker and the mechanisms to be able to absorb more energy without reacting as though a short circuit event was occurring. The realisation came from trying to go from a 400 amp device to a 630 amp device. Now, these are physically the same device, only with additional contact dimensions, things like surface area and silver and other bits and pieces and current carrying capacity within the circuit breaker. The 630 amp device we tested was an electronic breaker. So initially this breaker was successful in not tripping. However, after a number of DOL starts on site, the breaker developed an internal arcing fault that rendered it inoperative. The discovery that the electronic overcurrent relay was not detecting enough energy let through in the time it took to calculate and fire the magnetic hold trigger, this was a bit of a light bulb moment. Our conclusions were then proven correct, and the breakers were experiencing contact repulsion with each start. However, the electronic OCR was not forcing a trip. The mechanical reaction of the short circuit coil and the shot pin in the thermal magnetic type, however, was induced with enough magnetic force to maintain velocity and momentum to contact the latching mechanism and to trip the contacts. The remedy seems easy. Just increase the size of the breaker and the problem solved. Yeah, sure. But along with the requirements of Type 2 coordination in the mining industry, protection devices and the motor control equipment, any change in the breaker type or characteristic, a corresponding resizing was required for the motor contactor. Now, this was due to the probable increase in the let-through energy and peak let-through during short circuit events, potentially destroying the contactor and overload set. The replacement was a requirement of the standard. However, when we consider the ratings of the contactor to correctly size it based on pre-MEPS figures, it makes good sense to do the same to the contactor these days to avoid possible catastrophic failure or unexpected breakdowns during production cycles, not just based on whether type 2 coordination is required or not. Because we're subjecting the smaller contactor to the same or more forces, then it's probably not a bad idea to increase its size, to increase its reliability and its duty factors. So, do we have to upgrade the motor overload protection? Well, this is going to depend upon a number of factors. Number one, if the motor circuit tripped later than about 2 seconds after the start was called for and it tripped the overload. The most probable cause would be that the motor continued to draw close to locked rotor current for too great a time. Now, this may be caused by lower starting torque of the motor, not allowing acceleration to reduce the locked rotor current, not allowing the load to get away. So, in other words, stalling during the load's run up, and this can cause excessive currents to go through the thermal overload and cause a thermal overload trip. The inrush current does not cause a thermal overload trip. The other reason is if we need to comply with type 2 coordination. With thermal overloads, the answer may be yes, but consult the relevant coordination tables to confirm the need to conform to type 2. In many cases, electronic overloads do not need to be upgraded unless the frame size of the contactor that we've chosen doesn't allow the overload to be direct mounted or it's not a surface mountable type. So let's look at a few possible remedies that may be useful or may not be useful. Reduce voltage starting. Well, this certainly does resolve the issue of the current inrush and reduces the stress on the switchgear connected. The issue to be very aware of is that the reduced voltage starting of the torque of the high efficiency motor. In many applications, the torque produced by the motor may be marginal in accelerating a load on DOL anyway. If we use a star delta voltage reduction method, 58% of the voltage in star connection, the torque will be reduced by the square of the voltage reduction to roughly 30% of the torque availability. The same is true of electronic soft starters. They basically are a reduced voltage starting method, which is a smooth transitional way. So can we connect an impedance in the line? Well, you can, but this is similar to a reduced voltage start. A reduction in torque will be the result, and of course, if the impedance remains connected after the start, there's going to be a reduction in the system efficiency. So is the motor really worth the extra money if it can't be returned by electrical efficiencies? Do we increase the connected equipment capacities? Well, yes, this has proven to be successful. However, it may be expensive in relative terms, especially in smaller kilowatt applications. So we connect via VSD? Yes. Well, the VSD, this is the most successful method of overcoming the problem of the motor start. It also gives good torque control throughout the start and run process. The VSD itself, however, is not 100% efficient. So if we connect a VSD to a motor that runs constantly at full speed, it sort of defeats the purpose of using a motor that was designed to improve the previous models by 1% when we have an efficiency of an inefficiency of more than 2% out of the variable frequency drive. So these are all of the things that need to be considered. IE3, IE4 motors are not compulsory in Australia. MEPS 2 is the performance level that is required, or IE2 is the performance level that's required by the MEPS system. So in conclusion, we need to be aware of all of the issues. Circuit breakers may trip. They do so for a good reason. So we've got to consult the motor specifications before choosing the protection and control equipment. We need to consult the manufacturer's tables for appropriate combinations of the circuit breaker, contactor and overloads for the application. You need to be aware of reduced torque capabilities of high efficiency motors, especially for fan applications and heavy duty starts. When replacing an older motor, either consider rewinding or be aware that the existing switchgear may not be appropriate for the new motor. Always consult the technical information and manufacturer's recommendations. Failure to consider all of the factors may lead to a catastrophic switchgear failure, and this may have serious safety and financial ramifications. Okay, so look, we trust that this webinar has been informative and of assistance to everybody. If you have questions now, I'll be online for a short time to answer them. Otherwise, you can email me directly on syoung@nhp.com.au or call NHP customer service team on 1300 NHP NHP. Thanks for your time, and hope to catch up soon on another webinar in the future. Please direct your questions where you wish. Thanks for being here. Thanks for listening.
Hi Steve, Ron Pry here. Thanks for that presentation. Most of the questions which have come through during the session have been covered, so if there's no further ones come through, we've got one question come through live here. Besides motor starting by VSD, could motor starting using soft starters be capable of reducing the inrush initial currents whilst allowing for the motor torque and acceleration?
Thanks for the question there, Ron. Yes, look, as I mentioned during the presentation, soft starters can be used. However, they are load dependent, and the reason for that is they are not like a VSD. They are a reduced voltage method, pulse width modulator reduced voltage method of starting the motor. So effectively, it cannot increase the motor's torque beyond the rules of reduced voltage. So which the torque available reduces to the square of the increase of the voltage, or decrease in the voltage. So if we reduce the voltage to 50%, then we're going to get only 25% of the applied torque as a full load torque. So it's going to be dependent upon the acceleration curve required by the load for the motor to actually continue to accelerate under those circumstances. There are loads, of course, which are going to be okay with that, but most of the heavy duty loads will not put up with a low voltage start. I hope that answers the question.
I've got one other question come in. In general, do the thermal magnetic circuit breakers have a shorter minimum trip time than the electronic circuit breakers?
A shorter minimum trip time, a faster reaction time to a high level short circuit? The answer to that normally is yes. Under high fault conditions, we're not talking about just the thermal and the standard thermal and magnetic curves. We're talking about levels of short circuit above that which is graphed in their thermal magnetic tracing. The type B, which is the electronic, are designed to have that very small millisecond delays in there to allow for thermal magnetics downstream to operate under selectivity requirements. Having said that, the amount of time really doesn't do any harm to conductors downstream, which would be well within their withstands under those circumstances.
All right, excellent, Steve. Thanks for your time. We're sort of a little bit over, so just to everybody still online, the webinar, a copy of this will be posted on our NHP website, and you will receive a follow-up email with the link to that recording afterwards. So if there's a few questions which may still come out, but we'll respond to those, or you can send your email to Steve or via your local NHP sales representative. Thank you all for your time today.
Thanks, team. Have a good day.